Okay, so we're going to look at a new topic today, which is called haloalkanes, and this is an overview of the topic. And today we're going to look at preparation of haloalkanes from alkanes and alkenes, which we already have done. So this is going to be a bit of revision. So this will be useful for second years as well. And also we're going to look at a new reaction with alcohols to make haloalkanes. Later on in this topic, we're going to look at the main reaction of haloalkanes, which is hydrolysis. And also we're going to look at the environmental issues related to haloalkanes in terms of its effect on the ozone layer. Okay, before we do that, let's look at what haloalkanes are. Haloalkanes, as the name suggests, are organic compounds containing halogens. They can also be called halogenoalkanes or organohalogens. So you see these names in textbooks, but they all mean the same thing. They all mean haloalkanes. We are doing remote lessons because of this coronavirus or novel coronavirus, COVID-19. And at the moment, one of the possible cures, I guess, for the condition or this condition is being tested, and it's called chloroquine. As you can see from this structure, chloroquine contains chlorine. So effectively, this is, this can be considered or is actually a organohalogen. So if you're a second year, you recognize that these are benzene rings. So this really wouldn't suit the name haloalkane because this is not an alkane. This is not a aliphatic compound. Okay, so I'm going to do a bit of revision about what aliphatic means and remind ourselves what the difference between aliphatic and aromatic means in a bit. So let's look at some other examples. Obviously, this compound here won't be in the A level. We're going to look at some simple examples of haloalkanes, and we're going to name some of these. So this one on the left here, you can see it's based on methane, and there are 4 chlorines. So this is tetrachloromethane, and it's a common solvent. At the bottom here, we have a few more, and this one here has 1, 2, 3, 4 carbons, so that's based on butane, and there are 2 fluorines on the second carbon from the left and 1 chlorine on the third carbon from the left, or we can count the other way. So there's 2 possible ways to name this. So we can call this butane, and if we count from the left to right, it would be 2,2-difluoro. I'm going to give myself a bit more space. So 2,2-difluoro. And this is going to be 3-chlorobutane. Okay, or we can say this is 2-chloro, 3,3-difluorobutane. But we have lower numbers for the top one, so the top one will be a better option. The next one on the right here, I'm going to move these. The next one is based on cyclohexane, and there's a methyl group here, and there's the halogen, there's the bromine. So this will be called, will be based on the parent compound cyclohexane, or it will be methyl cyclohexane, and we have a bromo group. So since the methyl group should have the lowest number carbon. So this is carbon 1, this should be carbon 2. So we have 2-bromo methyl cyclohexane. Okay, one last one. So this one is going to be very similar to 2-bromo methyl cyclohexane, but instead of the methyl group, we have this group here, which is 1 carbon there, so that's basically methyl group, but we've got a chlorine on the methyl group. So this is chloromethyl. Okay, so this is chloromethyl cyclohexane with the bromine on the second carbon. So this is chloromethyl cyclohexane, and then we have the bromo group, bromine on the second carbon. Okay, so let's move on and look at the preparation of haloalkanes using alkenes. So this is revision, and then I'll introduce a new reaction today, which is the reaction of alcohols to make haloalkanes. Okay, so as we said, there are 3 different ways to make haloalkanes. One's from alkanes using halogen under UV light, so that's a bit of revision, and we do that in a minute. And we also have a reaction we already know, which is from alkenes using either halogen itself or a halogen halide. And the only new reaction is going to be this one here, using alcohols, and we use sodium halide and concentrated sulfuric acid. Okay, so the first one in terms of preparation of haloalkanes is halogenation of an alkane. So this is revision of a topic we've already done when we did alkanes, and it was one of the 2 reactions of alkanes. There are only 2 reactions of alkanes, and that's combustion, the first one, just burning the alkane, and the other reaction of alkanes is halogenation. There are only 2 reactions of alkanes for the A level. So let's look at halogenation of alkanes. So if I use chlorine, halogen, and let's say I use ethane, just a simple alkane, we have a substitution reaction where at least one of the hydrogens is substituted by the halogen. And to make it simple, the exam board expect you only to substitute one of the hydrogens in the mechanism, unless obviously they tell you otherwise. So we're going to substitute one of the hydrogens for the halogen. So this is going to be C2H5Cl. So I've kicked out a hydrogen, and the byproduct is a hydrogen halide. In this case, it's HCl. That's the overall equation. So the mechanism, as a revision, has 3 stages, and the mechanism is a radical substitution. Okay, and as we said, there's 3 stages. So the first stage is the initiation. So that is when the halogen-halogen bond, in this case chlorine to chlorine bond, is broken by UV light, as it is weaker than the carbon-hydrogen bond. So it's not the carbon-hydrogen bond that breaks, it is the halogen-halogen bond. So we write UV on the arrow to show the conditions. In fact, I can write it on the overall equation there. So we're going to produce 2 radicals. So we show radicals with a dot, and this is through homolytic fission. Okay, so homolytic fission is the breaking of a covalent bond. So you must say covalent bond in the exam, where one of the electrons in the bond moves to one atom forming the bond, and the other electron remains with the other atom that formed the bond. we take the radical, we don't have both of them, just one of them, and start our propagation step. So propagation means continue. So we have our chlorine radical, and we're going to have our alkane. So you may remember that the propagation steps, there should be 2 propagation steps, they add up to the overall equation. Okay, and I'll show you that in a bit. So you have to remember, this is the only thing you really have to remember, and the others you can really work out, that the first propagation steps give you this hydrogen halide. Okay, so I think I told you about the story when one of my students a few years ago was revising with me, and he made up this way of remembering that it's his hydrogen halide from the idea, we've got radicals and right-wing radicals might say how Hitler. Okay, so we have the hydrogen halide, how Hitler, as they say. So hydrogen halide. So once we know that, we can work out what's on this side by balancing this step here. Okay, so here we have a radical, non-radical. So we must have a radical here to balance the charge. So we balance by having a C2, 2 carbons, and we have taken one of the hydrogens away from the ethane, and we have C2H5. So this must be a radical because this hydrogen halide is in the overall equation. That's not a radical. That's part of that's the byproduct in the reaction, and it's produced in the first propagation step. So the radical is the alkyl radical. We take that radical from our first propagation step and we write our second propagation step. So as I said, that the 2 propagation steps, this one here and this one here, should add up to give us the overall equation. So we already have the alkane, okay, and we already have the hydrogen halide. So down here we will have what's left, which is the chlorine. Okay, so this must be the chlorine. Okay, that helps us remember what is in the second propagation step. And we must have the main product, okay, the chloralkane. So this is going to be C2H5Cl. So once we've done that, we're going to work out, there's a couple of ways of working out what's here, what's there. And that's either to balance this step here, or we have to remember that this is going to be a radical which is regenerated, so it's going to be the same as this chlorine radical. So it is actually the chlorine radical. Finally, this is the easy bit, which is the termination step, but you must remember to write at least 2 termination steps in the exam, even if you're not asked. So we're going to choose any 2 radicals, and they will pair up their unpaired electrons, and there'll be no more unpaired electrons, and we're going to have a non-radical. That's one termination step. We could have one of the alkyl radicals from our propagation from here, okay, with a halogen radical, a chlorine radical, to give us this product, which is actually the same as the main product. We could even have 2 alkyl radicals to give us a longer alkane chain, a longer chain alkane. So in this case it would be butane. And these are not the only steps in the actual reaction, because radical substitution reactions have many side reactions, and we get further substitution. We can get substitution at different positions. So you're going to get a very low yield of your desired product. So that's an overview of how you can make a haloalkane using alkanes, and this is revision, so you've done this already in the alkanes topic. So the next bit of revision and is the reaction of alkenes with either hydrogen halides or hydrogens to give us a haloalkane. So this is through a electrophilic addition mechanism. So this is a bit of revision of electrophilic addition mechanism. So I'll do a really simple example of ethene. So I'm going to use hydrogen bromide as an example of a hydrogen halide. So we join the dipoles. This is revision again, and the partial positive hydrogen will be attracted to the electron-rich double bond. Okay, there's a pi bond and a sigma bond in the double bond, and as it approaches, as this hydrogen bromide approaches the double bond, the electrons can transfer from the pi bond to the partial positive hydrogen. So the negatively charged electrons in the pi bond will be attracted, will move to a space between one of the carbons and this hydrogen. So it will no longer be in the space between the two carbons. As the electrons from the pi bond move towards the partial positive hydrogen, they're going to repel this bonding pair of electrons between the hydrogen and bromine, and it's going to move away from that electron density, and the only place it can go is towards a bromine. So we have that situation. So that's the first step. We now draw the intermediate. Okay, so we've broken the pi bond. There's no change with these hydrogens bonded to the carbons. And we can draw the hydrogen bonded to this carbon here or this carbon here because they're identical. So I'm just going to choose to draw it on the carbon on the right. I'm going to use red to show that bond is really, this bond here is this pair of electrons that has moved from the space between the two carbons to a space between one of the carbons, in fact this one, and this hydrogen. So it's now here. So there's the bond. So we have the bromine atom in HBr gaining that pair of electrons, and so gain of that electron is going to give this a full charge. This is no longer a partial negative charge. So this bromine is now a full ion, it's a full negative charge. Okay, it's not partial negative, it's a full negative. And we can even show the electrons it's taken from that bond, one of its own electrons and the electron from the hydrogen as a pair of dots on the bromine. Now this hydrogen here on the left here has lost the pair of electrons here, so it is now a positive charge. So you can draw a circle, you don't have to, but I tend to draw a circle to show up the charge. And this is, as we know, a carbocation. Okay, so this here is a carbocation. And finally, the electron pair from the bromide is going to move towards that positive charge, okay, because it's attracted to the positive charge. So that is going to mean the pair of electrons is no longer just on that bromide ion, it is shared now between this bromine and this carbon, and that gives the covalent bond. So we have a bond now formed between the carbon and the bromine, and there's our haloalkane, our bromoethane. Remember, if you got a asymmetrical alkene, you will get two different products if it was reacting with hydrogen bromide, because hydrogen bromide is an asymmetrical reactant. So I will upload a video on to remind you about Markovnikov's rule. If you've forgotten about Markovnikov's rule, how you predict which is the major product and which is the minor product if you have an asymmetrical alkene reacting with an asymmetrical reactant. But for now, I'm going to move on. So the next reaction of alkenes to form haloalkanes is using not a hydrogen halide, but use the halogen itself. Okay, so this is exactly the same mechanism, but instead of a permanent dipole on the hydrogen halide, we have an induced dipole. Okay, so this is a quick recap. So I'm going to use skeletal to just be a bit different this time. So I'm going to draw propene. Okay, so I'm going to use a halogen, so I can use bromine. So you've seen this in year 11, testing for alkenes using bromine, some of you. And this time the bromine is non-polar, so there's no permanent dipole, but as the bromine moves towards the alkene, the electron-rich double bond is going to repel the electrons on this bromine towards the other one. So I'm going to get an induced dipole. So this bromine here, closer to the double bond, will have will be electron deficient because the electrons are going to move towards the other bromine, and that's an induced dipole. And everything else is very similar or exactly the same as the previous mechanism. So I have electrons from the pi bond. This pi bond, which is electron rich, is going to be attracted towards this partial positive bromine, and it's going to move from the middle of the top pi bond. Make sure it comes from the middle of the bond. If it doesn't come from the middle of the bond, you'll be marked wrong in the exam. As these electrons approach that bromine here, the bonding pair of electrons here are going to be repelled away from that, and the only place it can go is this bromine here, and it's the only time you will see an arrow moving towards a partial negative or negative charge. So we're going to move on. That's our first step. Okay, so we've lost the pi bond, and the bromine can be added onto this or this one. Okay, and in this case it doesn't matter because the next step will be a bromine added to the alternative to the other carbon, and we get the identical product. So I'm going to put the bromine here. So there's the bond that was formed by the movements of electrons from the pi bond of the alkene to the bromine, and we have a bromide ion because this pair of electrons here has moved and been taken by that bromine atom. It's no longer an atom, it's a full ion. So not a partial negative, it's a full negative. So finally, before we do that, this carbon here has lost the pair of electrons, so it will have a positive charge. And we have movements of electrons from the bromide ion to that positive charge, from the bromide ion to the positive charge. And we have a bond formed between the carbon here and the bromine, because the electron pair now is shared between the carbon and the bromine, or bromide here. Okay, so that's 1,2-dibromopropane. So this is revision of electrophilic addition. So this is electrophilic addition mechanism. Finally, for today, for this video, we're going to look at the preparation of haloalkanes using an alcohol. So this is a new reaction we haven't done before. for the first years anyway. So what we have is we have an alcohol, so we choose, it can be any alcohol. We're going to choose propan-2-ol. Okay, so first years, don't worry about naming the alcohol. We will do alcohols later. And we have hydrogen bromide. Now this hydrogen bromide, we don't just add to the alcohol, we actually make it what we call in situ. So I'll talk about that in a moment. And we get substitution. We substitute the hydroxyl group. So we have a substitution. We substitute the hydroxyl group with the halogen. So we have a halogen here. Okay, so this OH then will combine with the H here to give us water, so to balance the equation. So that's really the reaction. However, as we said, we don't just add hydrogen bromide to the alcohol. This hydrogen bromide is made in situ. So the hydrogen bromide is made in situ, which is Latin. So the reaction that makes this HBr is as follows. So we use sodium bromide in this case to make the HBr, and if we use, if we wanted HCl, we use sodium chloride and so on. So we use concentrated sulfuric acid with the sodium bromide to make the HBr in situ, and we get a byproduct. Just by balancing the equation, what's left over is a hydrogen sulfate, and this is sodium hydrogen sulfate. So the sodium bromide can be a solid, it's ionic, and we know this is an aqueous solution because it's an acid, the sulfuric acid, and because we're adding a solid to a solution and the ionic compounds we dissolve, it's not a precipitate, that's aqueous, and HBr is very soluble. It's a hydrobromic acid effectively. So the HBr is made in situ. So we can add this equation here with this equation to give us the overall equation. So I'm going to list everything on the top equation and everything on the bottom equation. Okay, and we can cancel out the HBr on the left with the right. I'm just going to rub them out. So this effectively is the overall equation for the reaction. And the conditions for this, we add the alcohol or mix the alcohol with sodium halide with concentrated sulfuric, and we heat it under reflux. So this is going to be sodium bromide and concentrated H2SO4 and heat under reflux. So this is a reaction condition you need to learn. Okay, that's the only new reaction we're doing today on this video. Okay, as a reminder, especially for second years, that organic compounds can be grouped into two main types, aromatic and aliphatic. Aromatic just means that there is a benzene ring, so the first years won't know what a benzene ring is, but the second year will. A benzene ring is basically 6 carbons and 6 hydrogens. It can be written in this format or this format. If you don't know what benzene rings are, if you see either of these, that's a benzene ring for now. We'll cover that in the second year topic later. So this is C6H6, which is not the same as an alkene, although it looks like an alkene, it's not an alkene, as we see in the second year. And aliphatic compounds are basically non-aromatic compounds. They're just all the compounds which don't contain benzene rings, so we can call these non-aromatic compounds. And of those aliphatic compounds, we can group those into non-cyclic. So things like, straight chain alkanes or even branch chain alkanes, or even alkenes which have straight chains or even branch chains. Okay, so these are all non-cyclic. And the other possible aliphatic compounds are cyclic, and we met, cyclohexane, that's alicyclic. Okay, so anything with a cyclic ring is going to be alicyclic. Okay, if it's an alkane, or you can even have alkenes which are alicyclic. So, for example, that's cyclohexene, that's alicyclic. So, not to be confused with the aromatics. Aromatics are not like alkenes. Okay, we will find out. We will discuss this in the second year. So there's a bit of a recap of different types of organic compounds, or how we can classify organic compounds.